My name is Kotrina Gajokaitė. I am a statistical consultant at UCLA. I work at the Office of Advanced Research Computing. This seminar is Introduction to Directed Acyclic Graphs, other known as DAGs, for causal inference in R. And although I will be showing some code in R at the very end of the seminar, the bulk of it will be really learning the ideas of DAGs and how to use them for causal inference. So even if you're not an R user, I think you can learn a lot of sort of important foundational ideas about causal inference. So in this seminar, I will cover some basics of DAGs. Then I will discuss some elemental confounds to understand really how confounding works. And then we will talk about backdoor criterion method as a way to deconfound. And we're mostly going to think about linear models in this seminar. Then I will go through a couple of examples to apply the ideas that I discussed. And at the very end, I will discuss how you can automate it and basically do everything we will discuss in R. And then I will discuss briefly how you can do it even with AI such as ChatGPT. Let's start with this New York Times article that was published in 1981. And the main idea in the article was that people who drink coffee have a substantially higher chance of developing pancreatic cancer compared to those who don't. And if one is, reading the paper in 1981 in the morning, drinking their coffee, they might think, should I stop drinking coffee? And what I want you to notice that this question is really a causal question. In other way, you can think of it as it's asking, does changing our coffee drinking habits, so intervening on our coffee drinking habits, would that change our chances of getting pancreatic cancer? And of course, New York Times was very careful to talk about it as an association and not discuss it as a causal relationship, because after now many, many years and more studies and people thinking about this and looking at the data, we can say that it's not very likely that coffee is the cause of pancreatic cancer. And one of the reasons is that there was a huge confounder, smoking. So we know that people who smoke are more likely to drink a lot of coffee, and smoking itself is well established as a risk for pancreatic cancer. So later studies that looked at this relationship, collected more data, and accounted for smoking, this apparent relationship between coffee and pancreatic cancer pretty much disappeared. We might also then think, well, was this initial finding wrong? And it wasn't wrong, it's just answered a very specific question. And this question is, are coffee drinkers more likely to have pancreatic cancer? And that is true. The coffee drinkers, in the interpretation of the data at the time, were more likely to have pancreatic cancer. But what I was asking at the very beginning of this seminar was a very different question. I was saying, if I stop drinking coffee, if I intervene on my coffee drinking behavior, will my risk of pancreatic cancer decrease? And that is a causal question, right? Is coffee actually causing pancreatic cancer? And these kinds of associations reported in the news in 1981 cannot really answer causal questions that we might want to answer. And classical statistics has a long history on focusing on association rather than causation. Its main goal is mostly to summarize the data, and it doesn't even have language for causal claims. And at least as of today, no machine can really derive explanations just from raw data, just giving computer raw data and it giving you back the causes. At least today, it's not really possible. We need something else. We need something extra. And that's what the seminar is going to be about. What kind of tools can we add in order to be able to answer these causal questions? And mostly, I think, because most of research questions that we're asking, we are often interested in causal relationships. We usually want to know how the world works, and that is a web of relationships and causes and outcomes. And we need to be equipped to answer these questions. And interestingly, if we look at statistics, even with its long history of kind of putting causality away, it still uses some language that implies causality. So think about like dependent and independent variable. There is some relationship, of cause and effect that can be kind of interpreted. And of course, people have done causal studies, sort of like studies that, made causal claims, and experiments are really the gold standard for causality. A well-designed experiment, or we can call it a randomized controlled trial, what it really does, it enables these interventions. So these questions that I was presenting at the beginning, if I intervene, if I change my coffee drinking behavior, what will happen to my risk of pancreatic cancer, right? These experiments really enables us to establish this cause and effect relationship. And it has a secret weapon, this wonderful thing, randomization. So if we are, let's say, just creating two groups in our experiment, a control group and the group that receives some kind of exposure, any confounder that is measured or unmeasured will be equally distributed across these two treatment and control groups if we randomize assignment, because this randomization really breaks the ability to make one group different from another on anything other than the treatment, right? So it's kind of like a wonderful feature of the universe. Randomization eliminates confounder bias by ensuring that treatment and control groups have no systematic differences. There's only one difference between them, and that is treatment, right? And that's how we can establish that there's a cause and some kind of outcome relationship. However, people who study causal inference would want to suggest to all of us that experiments are just a special case of deconfounding. So causal inference is all about thinking about how can we make sure that our inferences are sort of about causes and are not confounded by some other variables like smoking in the example at the beginning of the seminar. So how do we deconfound? And experiments are one way to achieve it, but really it's not inherently superior. And experiments have some major drawbacks. Often they're not possible because, for example, intervention may be physically impossible. So think about an example where you study effects of body weight on heart disease. You cannot just randomly assign patients to groups based on higher and lower body weight, right? That's just impossible. Or it might be actually unethical to intervene in certain ways. So let's say we study smoking. We cannot randomly assign people to smoke for 10 years. It's unethical and kind of just straight, plain weird, right? We would not do something like that. So experiments are not really answering a lot of interesting questions that we might have. And then sort of as another type of data we have comes from observational studies. And these studies are just rich with all kinds of information. And because these data are collected in natural habitats, so there's no kind of artificial lab setting anything in it. It's, we observe things as they happen in the real world. So it's very rich and has so much potential. If we can deconfound observational data in any other way, you don't necessarily need an experiment then for causal inference. And here comes Judea Pearl, one of the most important scientists in causal inference, but of course he is not alone. He has a lot of students, collaborators, and there are a lot of other people who are working in this field and developing it very, very rapidly. But most of what I'm going to discuss in the seminar is based on Judea Pearl and his collaborators' work. So let's ask that question. Is there a statistical procedure that mimics randomization, right? if we cannot randomize in observational data. What Judea Pearl and his colleagues did, they developed something called due calculus, which is a formal set of rules that allows us to determine whether and how causal effects can be identified from observational data by mathematically transforming expressions involving interventions, or what they call due operators, into purely observational probabilities. We're not going to delve into the depths of due calculus, but we're going to learn logical rules, it's a formal system, and we're going to take them and learn them through backdoor criterion. This will be the focus in this presentation. However, backdoor criterion is not the only way to do causal inference with observational data. It sometimes cannot actually solve the problem you're trying to solve. So there are other methods also developed by Judea Pearl and his colleagues called front door criterion. Also, there are other things in causal inference literature developed by many different talented people, such things as instrumental variables as well. But we're not going to discuss them in this seminar. So the plan of the workshop, I already briefly discussed it at the beginning, but first we're going to talk about DAG basics. What are directed acyclic graphs? Basically, what are heuristic names for variables and unobserved variables and so on. Then we're going to talk about 4 elemental confounds. So these are your building blocks. Luckily, there are not so many different kind of ways that variables confound each other. That's a very lucky feature, I think. And then once we're going to cover that, then we're going to discuss backdoor criterion, which is a method of deconfounding. So first you need to know how confounding works, and then you will learn how to actually deconfound a DAG using backdoor criterion. Then I'm going to cover a couple examples, kind of put all these ideas into actual practice. And at the end, I'm going to discuss some software. So let's talk about some basics of directed acyclic graphs, or DAGs. They're basically a heuristic representation of a causal model. It's a simplification of some system that you might be interested in. What you have in them basically is they specify which variables influence others. So you can think of which variables listen to other variables. So for example, here's a simple DAG, and Z has a pointed arrow to X, which means X is listening to Z, or Z is influencing. The causal arrow goes from Z to X. Z is influencing X. And the great thing about DAGs is that you don't really need to make any assumptions about the actual functional form of the causal relationship, nor what kind of distribution of these variables, might be. All you have to assume is this causal direction. So here are some basic assumptions that most people use that you will see in the literature. So the letters represent random variable like X, Y, and Z. U, especially if it has a like a circle around it, typically represents unmeasured variables. And you often want to think about what are unmeasured things that also are important in this causal relationship structure, and add those because that will inform some of your decisions later. And as I mentioned at the beginning, these arrows denote direct causal effects. So for example, X causes Y in this example because there's an arrow from X to Y. Z causes X because there's an arrow. Z doesn't directly cause Y, and Y doesn't directly cause Z because there's nothing directly connecting them. There's some indirect links, of course, and we'll discuss those later. But it's also important to think, which variable affects which variable, but also, where are those direct influences absent. So once you assume a DAG, and that actually might be the hardest part, or one of the hardest parts of your project, is actually assuming how do these relationships work out? Like, can you actually put them on the paper. But once you have a DAG, you can analyze it to deduce appropriate statistical model for causal effect of X on Y. And throughout this presentation, I will mostly use Y as an outcome and X as the exposure of interest. But of course, it can be any other variable. And what the DAG can tell you using backdoor criteria that we'll introduce very soon, it can tell you which adjusted variables to include or which variables you can think to control for. As I said, we are thinking mostly about linear models here, linear statistical models. So what are other covariates I have to include in the model as a control variables to really deconfound the relationship between X and Y. And I'm going to say right away that, the common practice is to include almost everything you have in your data set. It's absolutely not safe to do it, and you will understand that soon when we're going to look at these fundamental confounds and how they behave, because sometimes adding a variable actually can hurt your inference. And here's a slide I borrowed from Richard McElrath's wonderful Bayesian course, where he also talks about causal inference. And I think it's a great illustration for these four elemental confounds. Luckily, there's only kind of four basic way variables behave and confound relationships. If you understand them really, really well, everything else kind of comes from this. And even, another good piece of news is that really the fork, the pipe, and the collider are the main three ways. The descendant is already kind of derived from these three relationships. So now we're going to spend some time understanding each one of these elemental confounds, and that will later help us to understand how to deconfound. Let's start with the first very basic confound, the fork. And to understand it, we're going to start using DAGs. So here's a very simple DAG that illustrates the fork. And this is what I mean by it, right? We have three variables, X, Y, and Z. And there's a causal arrow going from Z to X and from Z to Y. But notice there's no direct causal link between X and Y. X doesn't directly affect Y, and Y doesn't directly affect X either. But they do share this common cause, Z. So if we looked at X and Y and we wanted to know if they're correlated, they would be statistically correlated, even though there's no direct causal link. I just show you the DAG, right, that we're assuming. And if we ran a linear model predicting, let's say, Y using X, and we controlled for Z, so we counted for Z, included as a covariate, right? The spurious association that we saw at the beginning, correlation between X and Y, will be eliminated. So we're going to build on these ideas more. I'm going to give you a couple very simple examples to build your intuition, and then we're going to look at some simulation and to actually look at how it behaves. So first simple example is, think of this relationship. We have a child's shoe size. It is affected by age of the child. As children age, their feet tend to grow. They have larger shoes. Also, children's reading ability is affected by their age. As they grow older, they tend to become better readers. There's no relationship between shoe size and reading ability, right? Shoe size does not affect how well a kid reads, and reading ability does not affect a child's shoe size. However, if we looked at the correlation between shoe size and reading ability at various ages of the, like at the population of kids that are various ages, we would see a correlation there, but it would be spurious, right? It's not causal relationship. Those things are not, causing one another. So age of a child is a confounder here, right? Is the common cause, is this Z variable. If we account for Z, and basically, in a linear model, that would mean kind of looking at children of the same age, the relationship between shoe size and reading ability would be gone. Another kind of popular example is ice cream consumption, temperature, and violent crime rates. So there's this, you can find various representations of correlation between ice cream consumption and violent crime rates. So what is going on? It's clear that ice cream is not causing violent crimes, or that violent crimes is not causing ice cream consumption. It's all confounded by temperature. So some of the mechanisms could be, when temperature rises outside, it's hot outside, more people go outside, it's very hot, they tend to eat more ice cream, and perhaps there are more interactions, both positive and negative, and there are more possibilities for violent crimes to occur, or maybe heat even induces some kind of greater aggression in some people, and that's why violent crimes occur. But the point is that the correlation between ice cream consumption and violent crime is just purely spurious. It's not a causal relationship because they share a common cause, and that common cause is temperature. So now let's look at a little bit of code and how you can kind of study these elemental compounds and convince yourselves that you understand how they behave. So here's the same DAG that I presented before. Z affects X and Y. And here's a very simple simulation. There are various ways to of course, represent this in software, but here's one of them. So I use a set seed just for reproducibility. If you want to reproduce my results, you can copy the code here. The link to the notes is going to be in the description of this video. So we're going to set seed. We're going to simulate 300 cases. And I typically think about this, if I start simulating a DAG, the first variable I'm going to simulate is a variable that has no causes. You can think of it like exogenous variable. There are no causes coming into this. And Z is that variable. Nothing is affecting it. So I'm going to make a Z a binary variable, 0, 1. And so I'm going to use our binom function, with a trial of 1 and probability of 0.5. So we should get about, 150 zeros and 150 ones, like roughly, right? Then X and Y both depend on Z. So Z affects X and Z affects Y. So here's the logic here. I'm going to make those continuous variables. They don't have to be. It's just easier to kind of illustrate what I want to illustrate. So that's why I'm using continuous R norm function. And I'm going to sample 300 observations. But each observation will be drawn from a normal distribution. But the mean of that distribution will depend on the value of Z. If Z is 0, the mean of the normal distribution will be -1, standard deviation 1. If Z is 1, the mean of normal distribution will be 1, right? 2 times 1 minus 1 will be 1. So basically, you can think of it depending on what value of Z is on that row or in that spot, the observation of X will come from a different X distribution. And the same for Y. So now we can see how basically X and Y are both influenced by Z, but I did not build any relationship between X and Y in this, right? So then I can make a data frame. Here's like first 3 observations, so you can kind of see. And now I'm going to show you some plots. The plot code is here as well, but I'm not going to go through it. This is just a basic ggplot code. But what I mentioned at the beginning, if 2 variables share common cause, like Z, and if we fit a linear model where I predict Y using X right here, I can see that there's a correlation between them. It looks like as X increases, Y also tends to increase. But there's no causal relationship here, right? We built this ourselves, right? We did not build in any relationship between these 2 variables. All of that is coming from the common cause. They both have some information about Z, and that's what they're sharing, right? That's where the correlation is coming from. So to deconfound this, we need to control for this common cause. So I fit another model where I predict y using x, but now I also include z as a covariate, as a control variable. And now you see that the black line is the same line as you just saw before. So I'm just going to go back for a second. That's the same line. But now within each value of z, the relationship between x and y is essentially flat, right? So controlling for this confounder eliminates the spurious association between x and y. So this is how the fork behaves. Another elemental confound is called the pipe. It also is often called chain or mediation. So here is a simple DAG representing the pipe. So now X is affecting Z, or Z is listening to X, and Z is affecting Y. So again, there's no direct arrow pointing from X to Y. But if we looked at the correlation between X and Y, they will be associated because the X is transmitting some causes to Z, and that is transmitting, to Y. If we account for Z, so if we included, let's say, in a linear model as a control variable, the association is eliminated. Another way to think about it, and this will become more and more important, I think, once we go to exercises, this path X to Z to Y is an open path, right? If we control for Z, we close this path, right? And if we control for Z, account for it, there's no association between X and Y. You can also think of it that the mediator Z kind of screens off information about X from Y. Here is an example. So we have these three variables: smoking, lung damage, and shortness of breath, right? And we know that smoking affects lung damage, and lung damage affects shortness of breath. If we look at the population, smokers, will have higher probability of having shortness of breath than non-smokers. However, if we account for lung damage, the relationship between smoking and shortness of breath will disappear. And this is because basically once we know if a person has lung damage, there's nothing, smoking doesn't give us any more information, because in this particular case, the way I set it up, right, that smoking affects lung damage only, affects it directly, and then lung damage affects directly shortness of breath. There's no way for smoking to affect shortness of breath through any other path, right? So controlling for a mediator, lung damage in such a chain will eliminate the relationship between smoking and shortness of breath. So let's simulate again. Here is our DAG from previous page, right? So X affects Z, Z affects Y. And simulation is very, very similar. We're going to make 300 cases. Now, in this case, Z is the variable that is affected by X, and X is the one that actually has no influences from anywhere. So we're going to sample X first. I'm keeping it as a continuous variable, so we'll sample from normal distribution with a mean 0 and standard deviation of 1. Now, since Z depends on X, I'm still keeping it as a binary variable, 0 or 1. So I'm going to use our binom function. And now I set up the probability of success. Before it was 50-50, right? Because it didn't, depend on anything. But now the success will depend on X, and I'm using this function plogis for that. And basically, what this does is if X is greater number, the probability of success will also be higher. And then Y, as previously, we're going to sample from a normal distribution, and the mean of the distribution will depend on the value of Z. And here are a couple of the values of the data set that I will end up with. And now let's plot it again. So if we plot like before, where we model Y as a function of X, so X is predicting Y. We see that there's association between these two variables, although there's no direct causal link between them. Only through Z we have influence of X on Y. And as before, if we include Z as a covariate, we will see that that relationship disappears. So the black line, just to remind you, is the same line as in the previous graphs, but now these two red and purple lines represent relationship between X and Y within different values of Z. And you can see it's pretty much flat. There's some randomness, of course, involved, but it's pretty much non-existent, right? So we kind of recover what we assumed and what we built into the simulation. The third elemental confound is called a collider. And that's really what the nightmares are made of, is the colliders. Here's the basic DAG represented. So again, we have X, Y, and Z. And in this case, both X and Y affect Z. So X and Y don't directly affect each other. They share no causes, but they both influence Z, right? And the interesting thing about the collider, so remember in the pipe, I said the path between X, Z, and Y was an open path. The same was true also about the fork. If you have common cause like Z affecting both X and Y, that path is open, right? And to eliminate that association, we control for Z and we close the path. The collider is interesting because by default, the path is closed. So kind of causes kind of converge in the Z and they don't really, get out, right? So if we looked at X and Y, they would not be associated with each other. And that is true, right? That's the reality. That's what we assumed in this DAG. X and Y do not affect each other. They shouldn't be associated. However, if we find ourselves not sure if we should control for Z, we don't have any good kind of like theoretical reason to put it in or not put it in. So we just throw it in as a control variable. If we account for Z, what it does, it opens this path and X and Y becomes associated. That's where sort of the nightmare part comes in, that adding just any kind of control variable is not safe. Colliders will confound your inference and you won't even know it if you don't think through something like using a path diagram. So here are a couple examples to give you more intuition about the colliders. Let's talk about restaurant survival. I live in Los Angeles. Restaurants, most restaurants don't survive for a very long time, right? It's a very competitive place, but some of them do. And let's say these are toy examples, right? I just want to, underscore that. But let's assume that there are two main variables that affect restaurant survival. So food quality and location, right? Of course, restaurants that have great food quality and are in a great location are likely to survive for very long periods of time. However, that's very rare. Most restaurants kind of can maximize one of these dimensions. So, if restaurant is really, really, really good, they make really wonderful food, people will drive to, far locations just to try that food, and they might survive for a very long time. Other places that don't have great food, but are in great locations. So think about, like beach, somewhere at the beach, people come to watch sunset. They don't really care what kind of food they get, right? But location is everything. Or people watch something like Venice Beach, right, in Los Angeles. Location also can ensure the survival of the restaurant. If we were to look only at the restaurants that survive for a very long time, and this is where basically conditioning on collider comes in. If we're not taking the entire population, right, we're not sampling randomly from all restaurants that ever been there, but we're only looking at the restaurant that survived for a very long time, what we will end up seeing is that those who have great food quality will tend to be in bad locations, and those who have good location will tend to have bad food quality. There will be an association between food quality and location, but that's not true in the general population of restaurants. We see it because we accounted for a collider by only looking at the restaurants that survive for a long period of times. Here's another example, very similar. Again, I live in Los Angeles, right? Hollywood is here, so let's talk about actors. Let's say we are interested in successful actors, right? So let's say they've been in multiple movies that did really well. Doesn't matter, somehow we define the success, but it's something about, being in business for a long time. And an actor can succeed by having a really great acting skills and great physical appearance, right? So if somebody who has both of those attributes, most likely will do really well. However, it's really hard to have both of those attributes, and a lot of actors, will have great acting skills, but not necessarily great physical appearance, and vice versa, right? But if you look at all the actors out there, there won't be any association between acting skills and physical appearance. However, if we look at the success, and because success, let's say, depend on either acting skills or physical appearance, or both, but those are rare. So since those two skills are what gives you success, we will see this negative association again, that great actors will not necessarily will be conventionally have like certain physical appearance, and those with certain physical appearance will not necessarily have great acting skills. Again, and that happens because we're conditioned on a collider. Success in this case is a collider, right? We're not considering the entire population. Let's simulate a collider to convince ourselves that this is true. So here's a DAG again, right? X affects Z and Y affects Z. Very similar strategy, but now we're going to start with X and Y because no causes are coming into them. So we can just like sample normal distribution with mean of 0, standard deviation 1 for each observation. And then we make Z dependent on both X and Y. So probability of success now depends on some function that involves X and Y, right? And let's look what happens. The same strategy as before, but looks different, right? If we model Y as a function of X, I told you at the beginning, this path is closed. Everything collides at Z, so this path is closed. And if we look at the regression, like a simple regression model, right, there's no association between X and Y. And this is the truth, right? This is the true relationship between X and Y, because we know that we assume the DAG, and then we actually simulated the data based on it. Now look what happens if I include Z, which could be tempting. It's often tempting if you kind of don't have this kind of theoretical idea of how all the variables interact with one another. Could be tempted to control for this variable Z. And we add variable Z, and look what happens. So the black line represents the same line as in the previous graph. And now within each value of Z, we see there's a negative association between X and Y. So this could be interpreted as a causal association when we know for a fact that there's no causal relationship between X and Y because we built it in. Okay, so colliders are really, really terrifying, I would say, and they're common, and they can actually wreck your inferences if you just mindlessly add variables into your models. You can condition on a collider, so that the examples I was describing right here, food quality and acting skills, those are subsetting your data. You condition on a collider because you only look at the subset, but also that can happen when you include them as a control variable, because in essence, it's doing something very similar, right? It's looking at subsets of population and estimating relationships there. So colliders are very dangerous. So it's good to understand them and to know them and to look for them in your systems. Now, descendant is a fourth type, but really kind of it builds on the last three types. The basic idea is that descendant can be descendant for any, you can have a fork relationship, right, that we started at the beginning. You can have a pipe relationship, or you can have a collider. And descendant will be the variable that is descendant from fork or the mediator here or the collider here, right? So these are the descendants. And what happens if you, let's say, condition on a descendant, in this case, it behaves as if you somewhat conditioned on the actual parent here, right? So in the fork, it will partially eliminate relationship between X and Y. That's spurious. In the pipe, if you condition on the descendant, it will partially eliminate the association between X and Y, which goes through this mediator here. In a collider, if you condition on a descendant, again, it will partially open this path, right? This path by default is closed, will open this path and induce a spurious association between X and Y. So here's like just a simple example kind of to how you can think about when you can encounter descendants. So let's say you think, okay, there's a daily exercise that a person is doing. It affects their physical fitness, and then physical fitness directly affects their mental health, right? But then you don't necessarily have physical fitness measures, but you do have body mass index measures. And that is a descendant of physical fitness. So think of it as, if this is basically a pipe relationship that is just being described, right? This would be daily exercise X here. This would be physical fitness. This is mental health here. And the descendant will be body mass index right here. If we control for body mass index, we're kind of partially controlling for physical fitness, basically, because physical fitness affects body mass index, but there's not one-to-one mapping, right? Body mass index is not a perfect variable that captures physical fitness. So it will behave as partially controlling for that. And think about it, how common that is in research when we can't really quite measure something theoretical we need. So we measure something that is kind of like a proxy for it, right? Something that kind of captures it. And this is, in many cases, those will be descendants. And you have to kind of think about that, like you don't want to condition on descendant of a collider because you're going to partially open it. In some cases, you might want to do it. So it really, really depends what relationship descendant is representing. So let's bring it all together. We just discussed the four elemental compounds. This slide isn't just meant to kind of recapture everything we just talked. So the first one was the fork, where if we control for common cause, so the fork is represented right here, Z is the common cause on X and Y. If we control for Z, X and Y become deseparated. And this is, I just want to introduce this because you will see this in the causal inference literature, this notation, but basically you can read it. There's a key right here. X is deseparated from Y given Z, or conditioning on Z renders X and Y independent, right? Now for pipe, again, if we condition for the mediator, Z, X and Y become independent. So collider, if we condition on Z, in fact, X and Y become they're not independent anymore. They're conditionally dependent, right? So again, because in this case, for the fork and the pipe, these paths are open, right? And when you control for Z, it closes those paths. In a collider, on the other hand, the path is closed. And if you condition on a collider, it opens the path. And for descendant, as I mentioned, it really depends on the causal relationship. And these two upside down kind of T's just can be read as deseparation, or directional separation implies conditional independence and not deseparation. Once you understand the four elemental compounds that we just discussed really well, then you can start using Backdoor criterion method. And it's basically a method of identifying which variables should be accounted for or controlled for in order to block all backdoor paths. And backdoor paths, because these paths are the ones who are confounding the causal relationship. So that's what we're going to discuss right now. So to use backdoor criterion, you first need to assume a DAG, and that's perhaps one of the hardest things in a research project, to actually explicitly, identify which variables are important in the system and how they affect each other. Then you need to define the exposure variable, which I'm going to be always calling X here, and your outcome variable, which I'm going to be calling Y. And that, of course, is based on your research question. And if you're asking multiple research questions and you have multiple exposures that you're interested, for each one of them, you'll use the same DAG, but you will have to end up with a different statistical model. So to estimate the total causal effect of X on Y, you have to do three things. First, you will be identifying all paths between X and Y, causal and spurious, or backdoor. We're going to discuss in the next couple of slides what are these causal, spurious, and backdoor paths. And then you follow these following rules once you identify the paths. First of all, do not block or adjust for any variables on the causal path from X to Y. And that's because you don't want to eliminate any kind of cause, because we're interested in the total causal effect. And the second rule is you have to block all door paths between X and Y by conditioning on appropriate variables. So we're going to talk about what is a backdoor path, but remember what we're talking when we're talking about elemental confounds, that some paths can be identified as open, where information flows, and some paths as closed. So those are paths that contain colliders. Those paths are closed, so you don't want to open them, basically. Okay, so what are types of paths? Causal path, a very simple way to think about it, a causal path is a path where all arrows flow from X to Y. They represent how X affects Y directly or via mediators, right? So in this toy DAG right here, X affects Y directly, but also affects Y through C. C is a mediator, right? And then X affects Y through Z. Z is also a mediator. So there are three paths. So for a total causal effect, we want all those three paths to be open and flowing, right? We don't want to eliminate anything. Now, spurious paths, very easy definition, any non-causal path. So if the path is not causal, if you cannot identify a causal path, remember causal path will be either directly affecting the outcome or will go through mediators, right? If there's anything else along that path that might be not causal, that will induce association but not causation. So these non-causal paths could, like, information is flowing, right? But that is not a causal association. That is just a spurious association. So here's the same DAG, but a little bit modified. So X affects Y, X affects Y through C, that's the same, but now Z affects C, right? Z is a fork here, right? So this path is not a causal path anymore. This is a spurious path. Now, some spurious paths, not all of them, but some of them will be backdoor paths. And a backdoor path will be a spurious path, which is not a causal path, remember, that starts with an arrow into X. So we have one spurious path right here, Z points to X, and Z affects Y, and this path will be backdoor path just because of this arrow that's pointing to X, right? So here's a definition of all the paths. So when you identify all backdoor paths, each of them should be assessed to determine if it's open or is it closed. A backdoor path containing a collider is closed by default and should not be conditioned on. Conditioning on a collider opens the path, right? So if there was a collider anywhere, you don't touch that backdoor path. But if a backdoor path consists of forks and mediators, then it is open and should be blocked by conditioning on at least one of the variable along the path. So these are basically like logical rules that you can come back over and over again. But now we're going to actually put that into action. We're going to do some examples and we're going to try to apply these ideas. And you can see how you can do it basically by hand. And it's, I think, very, very important to learn it, to do it by yourself, to understand the logic behind it, and only then go into software and use software to do the rest for you. Before we do the examples, I want to remind you about this idea that we kind of started with, statistical trend versus causal effect, right? Something that's predicting something and something that's causing something is not quite the same thing. So let's say we have this very simple model here. This would be like a regression model. There should be error term, of course, here as well. But parameter beta here, you can always interpret it as an average observed trend, but it doesn't convey any causal relationship, right? That's the sort of the coffee and pancreatic cancer example. It's an observed trend, right? But it's not a causal relationship. This coefficient beta, however, can represent causal effect, but the data alone, right, just fitting this model on a lot of data won't reveal us when that relationship is causal and when it's not. We need some additional ingredients. That's what I started this with, right? I said, we're going to learn some additional techniques. So we're not dismissing, traditional statistics. We're going to use traditional statistics with something on top to help us do causal inference. And what you need is some kind of path diagrams. For example, we're going to be using DAGs and the adjusted variables, what I'm calling here Z, that satisfy backdoor criterion, basically that blocks all of those confounding effects, and then we can, get our total causal effect. Here's another way to illustrate it. If we assumed we have three variables, right, X, Y, and Z, and if we assume a DAG like this, where the X affects Y, but then there's a common cause Z that affects X and Y, in this model, if we want a total causal effect of X on Y, we need to include Z, right? Because first of all, we just learned a path that's pointing towards our exposure, X, is a backdoor path. Then we look at this backdoor path, it has a fork in it. Remember, if there's only a fork here, the path is open. That means we need to close this path. To close this path, we need to control for Z to deconfound, right? And we add Z into our model. Let's say we assume that there's no arrow going from Z to X, right? Now it changes. For the minimal adjustment set, and the minimal adjustment set, that means what are, the minimal variables that we need to account for or control for in order to deconfound, right? We don't need to include Z anymore because there's no that backdoor path. So we don't include Z. There might be more variables we want to include. It's not really the purpose of this sort of introduction course, but you might want to consider other variables because they increase precision and so on. But if we don't include them, we still should be estimating a true causal total effect if our DAG is correct, of course, right? All hinges on like how confident we are that we assumed a correct DAG. So with this in mind, let's do some exercises. We're going to start with this DAG right here, where we assume that X affects Y, but then there's something unmeasured. Remember, if the variable is U and if it's circled, typically it represents something unmeasured. So there's something unmeasured affects X, but it also affects Z, and then Z affects Y. Our goal is total causal effect of X on Y. And we're going to follow those three steps that I described before. So first, we're going to identify all paths between X and Y. And then we're going to make some decisions about each one of these paths. Is this path causal? If it's a causal path, we do not perturb it. We just leave it as is. If it is a non-causal path, a spurious path, is it a backdoor path? And if it is it an open backdoor path? Means it has forks or pipes. Remember, colliders close the paths. So if it's an open backdoor path, we're going to condition on appropriate variables. So first of all, let's list all the paths. There's direct path from X to Y, and then there's a path. When you identify these paths, you don't care which direction the arrows are pointing. A path is just a way to get from exposure to outcome, right? So you can go through X, through U, through Z, through Y. The first path is X on Y is a direct path, so that's a causal path, right? The second path through U is not a causal path because the very first arrow points at X. And if it points at X, that means that's a backdoor path. So I have to wonder now, do I have to actually close this path? Is it an open path? Yes, it is, because it consists of, here's a fork and here's a mediator, right? A pipe. So I need to control for one of these variables. I don't have U in this case, so that's no brainer anymore. I have to control for Z, right? Here's basically everything I said. There's one X to Y path, and then there's a path X, U, Z, Y. This is unmeasured, so I have to control for Z. So here's my solution. X to Y is a causal path. The second path is an open backdoor path, right? Because it's opened because it only consists of fork and a mediator, right? And that makes the path open. So I have to close this path by controlling for one of these variables. And in this case, I don't have U, therefore I control for Z. So my minimal adjustment set is Z in the system if I wanna estimate total causal effect of X on Y. It depends on the query, right? If I ask about like Z on Y, it will be a different solution. What we're doing is just asking from X to Y. Here's another example. It's a similar DAG, but now we have a mediator from X to M to Y. Again, let's identify all the paths. So we have a path X to M to Y, and then we have a path that goes through X to Z to M to Y. So they're all our paths. There are only two paths, how you can get from X to Y. Now this first path, there's a mediator, right? This is a causal path. I should not do anything to, should not touch it. Now the second path, because the first arrow, this arrow points to X right here, that means it's a backdoor path. Now I have to consider, is it an open or a closed path? In a very simple way, if it's a forks and mediators, that is an open path. So I have to control for one of these two variables. Now, I shouldn't control for M. And why? Because I will close this path. So sometimes, when you consider what to do with certain path, you have to also take into account what's going on with that variable in other paths. So I cannot touch M, but I can control for Z. So I'm going to control for Z. Okay, so the first path is a causal path with mediator M. The second path is an open backdoor path because of this arrow pointing to Z, and we can close it with Z, but do not control for M, right? So minimal adjustment set is Z. Another example, now we have two unobserved variables, U1 and U2, and they both affect Z, right? And then U1 affects X and U2 affects Y. So let's identify all the paths. There are really only two paths. You can go from X to Y, and then you can go from X to U1 to Z to U2 to Y. Here are the two paths, right? The first path, X to Y, is a causal path, so we don't touch it. I mean, there's nothing to do there, right? There's no intermediate variables, really. But then the second path, because U1 points to X, makes it a backdoor path. So now we need to consider, is it open or closed? And we see there's a collider Z. Z is a collider, so U1 and U2 collide in Z. And because there's a collider, this path is closed. So the solution for this particular DAG, when we want total causal effect of X on Y, is to not control for Z or anything really, because that path is closed. We don't have U1 and U2, and Z is the only thing that's available for us. We should not control for Z, even if it's tempting, and I'll show you a real-world example shortly where it might be tempting to control for Z or for a variable that's in that position as Z. And here's a final example. Again, we have the same goal, total causal effect of X and Y. These are just to remind you what are the rules. Let's identify all the paths. Now we have a lot of paths. So we have X to Y directly, then X goes through C here, then X goes through Z here, then X goes through A, Z, and Y, then X goes through Z, B, and Y, and finally X goes through A, Z, B, and Y. So here's a list of all these paths X to Y that I just basically listed. So now we're going to go through each one of them and discuss what to do. So X to Y is a causal path, direct path, all is good with it. The second path is an open backdoor path, and it's open because C is pointing to X, right? This path right here. And C is a fork. That's why it's open, right? How do we close a path with a fork? We condition on it. So we close it with C. Then Z, X, Z, Y is a very similar, right? The mirror image of C is the same situation. It's an open backdoor path because Z is pointing to X and Z is a fork. So to close it, we're just going to condition on Z. Then we have a path X goes through A, Z, and Y. Again, that is a backdoor path because A is pointing to X, and we have a fork and a mediator here, a pipe here, right? That makes it an open path. So we can close that path either controlling for A or Z. We have a choice, maybe sometimes, you might want to control, if the variable is more precisely measured, you might make a decision to control for that variable. Then we have a path X through Z through B to Y. Again, that's a backdoor path because B is pointing to X. And we have a Z and we have a B. B is a fork. There's a mediator here, Z. So it's an open path again. So we need to either control for Z or control for B. And then finally, we have this path X through A through Z through B through Y. And immediately you can see Z is a collider in here. It's a backdoor path. We have to consider it, but it's a closed path. We don't need to do anything about this path anymore. Don't touch anything. Basically, this is closed. However, there's a huge problem. And that huge problem is that we have to control for Z because of this path, this fork, right? So we already control for Z, so we open sort of this path already, right? We can't avoid that. But not everything is lost. We can close this path if we control either for A or for B, for these forks that are actually colliding in this collider, right? So we need to pick either A or B. So minimal adjustment set then is C, Z, those we cannot really escape, and either A or B, okay? Now I want to give you like a real life example from a paper. It's a DAG we just discussed, was our example 3. And it comes from a paper by Albert and Winship. It's a really great paper. It's a short one. It's a great read, I think. And the example is, let's say we have this DAG and we want to answer the question, does the civic engagement of individual 1 leads to civic engagement of individual 2 in a subsequent time period? So here's a variable that represents civic engagement of individual 1, and this is, we are hypothesizing that there's this direct relationship with civic engagement of individual 2. And then we know that what's affecting civic engagement of each person, sort of their own civic engagement, is we're going to call it something like altruism, right? Of that person is affecting how much one person is altruistic, how much another person is altruistic. We think there might be something, also in their interactions that make other person more civically engaged based on the first person. And we also have information whether they're friends or not, right? But altruism of one person and altruism of another person will also affect whether they're friends. Let's assume that people who are both are more altruistic are more likely to become friends, and people who are less altruistic are less likely to become friends. If we draw a DAG like this, and given what we just discussed, it's clear that there's one direct path from civic engagement to civic engagement 2. This is a causal path. And then there's the backdoor path through altruism, friends, altruism 2, and to civic engagement of the second person. It's a backdoor path because altruism 1 is pointing to civic engagement 1, right? But this backdoor path is closed because friends or friendship, whether these people are friends, is a variable that's a collider of altruism of the first person and altruism of the second person, right? So just given purely sort of what we learned so far, we should not control for friendship. And it could be very tempting if you have all this information about civic engagement with people, and then is this are these people actually friends, to control for it, and it would actually distort your inference. So here's a solution, right? It's the same solution as for the example 3. There's one causal path, and then there's this one backdoor path with a collider friends in the middle. It's a closed backdoor path because it's a collider. Do not do anything. Let me try to give you a bit more intuition about this. So let's say we eliminate, we know that there's no relationship between civic engagement of person 1 with civic engagement of person 2 now. There's only this backdoor path right here, right? So looking at this DAG, basically individuals may show similar civic engagement, not because one influences another, right? So we're assuming there's no influence between these people, but because similar individuals tend to form friendships, altruists, right, let's say, and they also because they share similar altruistic sort of tendencies, they also will exhibit similar civic engagement tendencies. So the common cause here, which is unobserved, right, drives both friendship formation and also drives each of them separately civic engagement. If we condition on friendship, which is a collider, it creates an association between civic engagement of individual 1 and civic engagement of individual 2, right? But we know there's nothing there. So we know there's no causal effect. But you could simulate it and show it just, with simple simulations like we did. Conditioning on this collider will make these two variables correlated when in fact, if you wrote your simulation correctly using this DAG, there's no relationship between them. If there is a relationship between them, this relationship will be distorted by conditioning on the collider, right? So this is where, kind of causal thinking and DAGs can really, really help in avoiding some disastrous sort of results that you will interpret later as causal that might not be causal. So we are coming to the end. I just want to reiterate the idea that I already presented. So if you're doing causal inference with linear models, and you have multiple exposures that you're interested, you will be designing a unique statistical model based on a DAG. So you'll end up with one DAG, but for each query you have about each exposure, you will do a different statistical model. And this is very important because of a table 2 fallacy. There's a great paper by Westricht and Greenland. These are all links. So if you get the notes from the link at the bottom of this video, you can get this paper. This is a really also great short paper. And the main idea in this paper that it's very common to present multiple adjusted effect estimates from one model in a single table. I'm sure most of you have seen, it's usually table 2. And it's important to understand, which hopefully you do after this presentation, that not all coefficients are causal effects, right? In a specific statistical model that's designed using, let's say, a DAG, there will be only one exposure variable for the outcome. The table 2 fallacy is actually misinterpreting these coefficients of control variables as causal effects and talking about all of them as causal effects, even when the model wasn't designed to estimate them, right? So read this paper and be aware of this mistake. Now, very briefly, this is, introduction to DAGs in R, but I think the bulk of this you really need to understand conceptually, and software here just comes to help you out. So I think it's very useful to be able to do it by hand, but sometimes you have so many variables or you want to just double check your work. And thankfully, this problem of deciding which variables to control for has been automatized in R and many other software packages. So I'm going to show you like a brief way how you can do this in R. So if you want to just basic, you have a basic question, what should I control for when I assume a certain DAG? You might want to use a DAGity package. I'm here using a C just so you can reproduce my results if you want to. And let me scroll. So the minimum you need is to specify causal relationships. And to do that, you just think about, dyadic relationships. So think about all the variables you have and which dyadic, pairs actually affect each other, and you list that. X affects Y, and, list which ones affect which ones. And here's sort of like the format of doing it. And that's all you need. Once you have this, I call it D, you can call it whatever you want, this object, then you can just plot that object. You can see what it looks like. It gives you sort of, sorry, my mouse is misbehaving. This might be not very pretty, not what you actually want, but you kind of can see how these variables affect each other. And then you can use this function adjustment set, where you list the object, where you just, that's your DAG, right? And then you specify what is your exposure variable. So X, for example, what's your outcome variable is Y. This is the DAG that our example 4. So we just discussed it with the collider in it, right? So we said it's Z, C, and A or B. So that's why it gives you two alternatives. Either use BCZ or use ACZ, right? So there are two possible solutions. Or you can say, I have another exposure variable Z, an outcome Y, and what is the adjustment set, and we'll give it to you. So it's all like the rules that we just discussed, these logical rules have been built into the package, and you can use it. Now, if you want to make something slightly nicer, something like that, you can use ggdag package. There's a code right here. So you can control the coordinates, for example, where exactly the nodes are going to be. And you can, make a plot. Basically, it's like a ggplot syntax with a little bit, different functions. Like instead of geom, you'll have geomdag, right? And here's the same DAG as above, just rearranged a little bit differently. And you can pick colors and do a lot of things if you're presenting it to an audience. And, the strong part of these directed acyclic graphs, if you assume one and if you use it to justify your variables that you include in your statistical model, you also, I think, want to put DAG into the paper so your colleagues can actually see your assumptions and you can argue about the assumptions and hopefully in that way science moves forward. There's a lot of other software you can use. So R has DAGD, but there's also this PC lag package, causal effect. Python has a couple of libraries, causal graphic models, and DoY. SAS has causal graph where you can do the same things. And there are these other websites like Causal Fusion. This is Judea Pearl and his student, and DAGD has actual website. Check out DAGD website. You can actually draw these DAGs kind of like with, maybe a bit easier to control if you don't like coding as much. Also, you can do causal inference using AI. So for example, ChatGPT. I will still assert that as of today, you can't really, give a ChatGPT a data set and it will not find causes for you in it. You need to give those extra ingredients. So something like a DAG, like a path diagram, right? And it knows the rules of causal inference, everything that I presented today. And it's really good in helping you to figure out what you should control for if you have a DAG and if you have, a question. You just need to kind of be careful, how you phrase things. So here, what I did, the beauty of AI is that you can use your natural language, right? You don't need to know coding in order to interact with it. But what I did, the prompt I gave here is what is the easiest way for you to understand, how should I present a DAG for you and a problem associated with it. And this is what it gave me. So, something like that's where you will list your variables. You, again, give edges the same way kind of you did in DAGD, right? And then you say, here's my exposure is A, here's my outcome is D, and what I want, draw me a DAG, it will draw you a DAG, and check if if the exposure outcome is identifiable using a Backdoor criterion, meaning what do I need to control for, right? So you can do that with ChatGPT as well. So this is the end. Here are some additional resources that I think are useful at the beginning, at least. There's a wonderful book, The Book of Why by Judea Pearl, written about you can find a lot of interesting history about statistics and causal inference and leaps it made in the last few decades. There's another book by Judea Pearl and his collaborators called Causal Inference in Statistics that's also really good. There's a wonderful paper, a crash course in good and bad controls by Snelly, Forney, and Pearl. It really discusses all these different DAGs and when to control for something. And I think if you want to go deeper, I mentioned like there's sometimes you have a minimal adjustment set, but then you might want to include some other variables because that will increase your precision. Your standard errors will be smaller, right? And this paper kind of goes through some of these examples. Another link to table 2 fallacy paper, which I think everyone should read because that's a very common kind of occurrence in at least in where I work. And finally, there's a great paper by Hernan it's called The C Word. It's about causality and sort of like how scientists are avoiding causality language when they seem to also desperately want to use it. So thank you very much for watching. My name is again Katrina Kayokida, and I work at UCLA at the Office of Advanced Research Computing. Thank you.